start.
So I'll skip 6 and we'll do that after Catalan and I'll just go to 8 and 9.
Yeah,
Okay, so do you want to share screen or should I?
I could share my screen. Do you want to see the problem set? Yeah, I need to find that. Wait, hold on.
You can, like, I'll just ignore the error in number 1 because it gets confusing switching back and forth between the US and the QS.
Could you see this?
Yeah, now I can see that. So we're just going to full screen. Okay, so
Oh,
start with number 1.
okay.
So on Monday, October 5th, 2256, the Earth's rotation got messed up in the story universe. The QSA elected the next president. Looking on the map, there are 30 sections, but 10 of them are. I know it says safe states, it's actually called safe sections in the QS, which means that they can only vote for one of the two parties, the castle or the palace. The other sections could vote for whichever party they want. How many ways are there to fill out the map? And sections cannot be split. So this is similar to on the Electoral College in the United States, but in the QS, we have 30 sections, but 10 of them we already fixed to be castle or palace. That means that the other 20 sections can go to either of the two parties. There's only two parties and there cannot be any ties. Therefore, each of the sections can make a choice between going to the castle or the palace. So that's two choices, and that is done 20 times. Therefore, the answer is 2 to the 20. There are 2 to the 20 ways to fill out this map. Number 2, Stone Mill Low School is going to have an intra-school Newcomb tournament. There are 8 teams, and in the first round, each team will face the other teams exactly once. How many games will there be? So if we have team 000, like the teams are numbered with 000001 all the way to 111. So team 000 will face off against the other 7 teams. And so will the team 001. However, team 001 already faced off against team 000, and therefore that would be counted twice. So you have 8 teams, they all face against the other 7, so that's 8 times 7. However, each each game is counted twice. Therefore, we have to divide by 2. So the answer is 8 times 7 divided by 2. Number 3. In the year 2218, the 9 major cities of the QSA were the capital / Hello City, The Cut, New Hope, Pennsylvania, Viva Gelahare, Ocean City, West Coast, Hexalo City, Hexalo, New York City, New York, Lakeview Lake Region, Suspense River Path, and Sea Atoll, Washington. They wanted to connect these 9 cities, with a railroad that went under the ground and a flight route. So how many connections will there be between these cities? And how does this relate to question 2? So I want to introduce something called the VHV correspondence, sometimes called one-to-one correspondence or bijection. So for each railroad, if we treat each of the cities as a team, like another Newcomb team, and the railroads are matches between the teams, then that matches perfectly. So each railroad corresponds to a match between the teams, and each city is like a team in a tournament. So from that we have 9 times 8 divided by 2. However, we also will have a flight route between those cities. That these are counted the same way as the railroad. So you just double the number. So 9 times 8 divided by 2 and then times 2, which is just 9 times 8. So question 4, if you click on that link, it should bring you to Ling Ling 40 hours.
Could you see this?
It says waiting for www.redditstatic.com. I don't
Um,
I don't know if that's a VPN issue or.
no, it's the sharing screen issue.
Oh, wait. Oh, I don't want to.
That's weird. Here. You could see this, right?
Okay. So this is on the Ling Ling 40 hours. So this, I think, this one we could use generating functions. We could do casework. We could do direct counting. Do you have a preferred method?
No, I know.
Okay. So
Do you want to use whiteboard or whatever?
oh, actually, this one really isn't that difficult.
Okay, right. All right.
So yeah, I read the question slightly incorrectly, but this one, what it actually is asking, because the 9 pieces are actually going to be all different. Um, so what you do is that you have 9 pieces. You want to choose 4 of them, so that's just 9 choose 4. For 2 pieces by Beethoven, one by Handel, one by Sibelius. So there's 2 ways to choose one from Sibelius, 3 ways to choose one from Beethoven, and out of the 4 from Handel. Out of the 4 from Beethoven, we want to choose 2, so that's 4 choose 2, and then you multiply that by the 3 and the 2. And there must be 1 piece by each composer. I think this one you can use casework again. So we already evaluated 1 case in 2 for where 2 pieces are by Beethoven. If 2 pieces are by Handel, then it's 4 times 3 choose 2 times 2, and then you add the case where Sibelius has 2 pieces, which is 4 times 3 times 2 choose 2. And that's this question.
Wait,
So,
let me here.
so number 5. So the Seattle staircase, it's 15 blocks on each side of the staircase, and those are 1 foot high. And the important thing is that each block's height is equal to the sum of the heights of the adjacent blocks that are closer to the origin. Now, I didn't really complete this, but on the other side of the, but they actually just reflected it on the other side, but it doesn't matter. So, so the technique that we want to use here is something called lock walking, and this also introduces Pascal's triangle, or however you pronounce it. So I'm actually going to go on to my screen where I have the. So yeah, I'm gonna go share my screen. Hopefully this is the right one. So, oh, we start here, and there's one way to go from here to here. Now, there's one way to go from here to here, and we're only considering paths that take us further away from the origin, and we can only go directly in this direction or directly in this direction, so we can't go this way. But there's one way to get here, there's one way to get here, there's one way to get here, and for all of these blocks, and remember, we're ignoring this half of it, we're only focusing on this half. For all of these, there's only one way to get to there. Now, to get to here, you first have to go get here or here, and it turns out that the sum of these two, that we can just add these two to get this. So there's two ways to get here. So if we start at any square, it's just going to be the sum of the two squares that are closer to the origin and adjacent to it. So it's this square plus this square. So what we can do is use a VHV / bijection. And what happens is that we have a string of this way is south, east, this way is south. So we have a bunch of E's and S's, and depending on how far we want to go in each direction, we have that many E's and that many S's. And then we will permutate them. And since the E's and S's are not going to be distinguished, like you can't tell the difference between them, like between each individual E and each S, it's going to be, then you also have to divide by the number of the E's and the number of the S's, and on the top you have the total number of E's and S's. So to get to this highest point, you have to travel 7 in one direction and 7 in the other direction. So that will give 14 choose 7 ways, which I believe evaluates to 3, 4, 3, 2. So you can see that it's 3, 4, 3, 7 and 0.5, but that's because the height for SketchUp, it'll default to being 5'6". So if you subtract that, then if you subtract the 5'6", that gives 3, 4, 3, 2, which is 14 choose 7, which is the maximum. Okay. So going to do you want me to do 8 and 9 first before you do 7 and 10, 6, 7, and 10?
8 and 9. I'm not going to do 6.
6 is an application of 10. So
yeah. So let me do 7 first.
So you'll do 7 and 10 and 6, and then I'll do 8 and 9 at the end? Or
I'm not going to do 6. I haven't looked at that yet.
So am I doing 8 now?
No, I am doing 7 now. Okay, let me share my screen. I hope you could see this. You could, right? So for 7, the question it's this. There are 33,333 students at Duncan University. And let us assume this number of students to be n. And because n is a odd number here, let us assume that n is equal to 2n plus 1, where m is any integer. No, any positive integer and 0. Some students join together to form several clubs. A student may belong to different clubs. Some clubs join together to form societies, just like Math Club and CrypNTo. A club may belong to different societies. There are a total of k societies, so notice another variable here. Suppose that the following condition hold. So first of all, each pair of students are in exactly one club. And secondly, for each student in each society, the student is in exactly one club of the society. And thirdly, each club has an odd number of students. In addition, a club with 2n plus 1 students, m being a positive integer, is in exactly m societies. Find all possible values of k. So before looking at how to solve this problem, let us look at an easier example of when the number of students is 3. So the condition 3 tells us that each club must have has an odd number of students. So there are 2 cases. The first case being each student has one club, and the second case being 3 students are all in just one club. But the first condition says each pair of students are in exactly one club, meaning that our first possibility is not possible. 3 of them must be in one club. And this satisfy the condition 1, condition 2, as well as condition 3. So the only case here would be this. We have 3 students. They're in just one club. And since they're in one club, we only have one club. So this club belongs to a society. Okay, so for this case of 3, when the number of students is 3, the solution is unique. We only have one solution. So could you make an assumption about what the solution might be if we change this number to 5 threes? So a possible assumption would be the solution is actually unique, and we're going to see that. Before getting into solving this problem, I'm going to introduce you some of the notations and definitions that I'm going to use. So I am labeling each student with a triple, ordered triple. Can I delete this? I'm using ordered triple because the order can't be reversed. A comma C comma S is not going to be the same as C comma A comma S. The definition is not the same as a set, and the notation is also different. And A represents student, C represents club, and S represents society. So we have several labels here. Each student is labeled with one or several labels because one student could belong to different clubs and they could belong to different societies. Now we're going to look at things from the conditions that we have. So what can we infer from the condition 2? Condition 2 is a very special statement. It says for each student in each society, the student is in exactly one club of the society. So notice how the condition is structured here. We have for each and exactly one, which means that if we let this number of students be n, just as what we said here, and let the number of societies be k, we have it here, then the total number of labels or the total number of order sets that we'll have would be n times k. And what can we infer from the condition 3? Condition 3 says each club has an odd number of students. And in addition to that, a club with 2n plus 1 students, it's in exactly m societies. So let us assume that the total number of students in one club be this. So from the relation here, we could infer that the number of societies would be this minus 1 divided by 2 for one club. So we're looking at the total number of order triple when the C is fixed. So for example, we have C1 here in S. So the total number of these these order triple would be this. And if we're doing, if we are counting all of them, we will have a summation of those. And so my third question is asking, what can we infer from the condition 1? Condition 1 says each pair of students are in exactly one club. And how many combinations, let us ask a question, how many combinations do we have? We have n choose 2 combinations because we are choosing two people, like a pair of students from n students in total. So that would be equal to the total number of the ordered set, which is the summation of, did I write something wrong? Wait, we have, okay, this is number of societies, and so that the total number would be this times this would be societies. Okay, so this is also from 1, we can know that this is also equal to nk. Now we have something very neat. We have n choose 2 is equal to nk. We're finding the value for k, so the k would just be, simplify this. K would just be n minus 1 divided by 2. So the case here, we're finding the k when n is equal to, that gives us k is equal to 4, right? Yep. Okay. So from this whole solution, we will see that our solution would be unique. The k there's only one k for each n, for each possible n. And maybe there are some deeper meanings that this question is trying to convey to us. And I do not know what are those. So it is something for us all to explore. Do you want me to talk about 10 right now? Or
Yeah, you can do 10.
okay. So question 10 is asking us to prove the Catalan number formula, and I'm going to write the Catalan number formula here. So we say that the nth term in Catalan number sequence is equal to 1 divided by n plus 1 times 2n choose n. And we were trying to prove this. So the Catalan number is coming from the number of non-crossing partitions for a n-ordered set. And let us try to understand non-crossing partition by using some visualizations. As we know, the classically numbers in discrete math, like natural numbers, are usually represented in either a line or a circular object. So for a line, we will have this here. We will have 1, 2, 3, and 4. For a circular object, we might have 1, 2, 3, 4, 5, and 6. So the word partition means that we're trying to divide this whole set up into several parts, and we do not have any repetition, meaning if we attribute 4 into one subset, then we can't attribute 4 into another one. And all the numbers should be used once and only once. Let me show you a crossing partition and also a non-crossing partition, and let us compare them to see if you could understand this. So on the left-hand side, I'm going to draw some crossing partitions, and on the right-hand side, I'm going to draw some non-crossing partitions. So for the linear one, here we have 1, 3 together and 2, 4 together. And here we have these 3 being partitioned together and these 3 being partitioned together. And here we also have 1, 2, 3, 4 elements. Here are 6 elements. Okay, so what characteristics that you could see that says the left-hand side is crossing and the right-hand side is non-crossing? Do you have an opinion? Forest?
It's like the lines, they don't intersect, so
Yes, right. So on the left-hand side, so for the arcs, for the linear objects, they have a intersection, and also for the part down here, the circle thing, we also have an intersection for the crossing partition, but we do not have an intersection for the non-crossing ones. So let us be more formal here. Can we derive something that describe what non-crossing partition means by using set theory? Okay, so my idea is that let us look at this term divide this term up into 2 parts. So firstly, we have the noun partition. We need to define the partition first. If we say that we're given a set with n elements, let this as be S, So the first element being A1 and then A2, all the way up to AN, and such that we have A1 smaller than A2 smaller. You could of course rearrange this, but just for the convenience, we're defining A1 is smaller than A2 smaller all the way up to 8n. We say that this set is partitioned into k subsets, meaning that we're attributing all the elements into k subsets. We name those k subsets as BIs, I being somewhere in between, inclusively between 1 and k, and we call those, they have a term, blocks, such that first of all they need to all the element in this set S should be partitioned in one set. That means all the things are taken up. All the block, the union of all the block will take up the whole set. Secondly, we say that each pair of blocks should not have an intersection pairwise, so that no element is taken twice from the set. Let's say that for any BP and BQ two blocks here, one is smaller or equal to P smaller than Q smaller or equal to K. Their intersection is empty. And thirdly, so the third condition here, these two conditions, all of these actually conditions here, help us to define what partition means. And the third one here is meant to define non-crossing. So let's go back to here. If we have only one element in one block, just like the case here, we do not need to worry about the crossing or non-crossing or anything like that. It will not be, it will not cross other things because it can't, if we're doing a like linear visualization, it cannot be, it does not have an arc in general. So the third case, we're only considering the case when the cardinality of our blocks is are greater than 1. So we're only looking at BP. And we say that for any BP and BQ, similarly, so I use this to represent the least element in the smallest element in the block BP, and this being smallest one in BQ. Can we understand this? Do we understand this? I take that as a yes. Okay. So let's assume that we have a linear thing like this here. So this being the smallest element, in block P, And we know that this is AP. This is AQ. So we're doing this. And we need this next. We need all the elements that are covered by BQ to land inside of the next element that this is going to reach. So this could be any element in the block, basically. Does the visualization look something similar? Yes, it does. It looks like the diagram in the problem set. So we have some several pentagons here. So the first block is all the non-crossing partition cases for a pentagon. And the second one would be the crossing partition cases. And this represents C5. And today we're going to use this to prove a Catalan number formula. And the way that we're trying to do that is by, first of all, increasing the dimension. So for this here, we're doing C5, the pentagon represents C5. And let us increase the dimension and by 2. So a m plus 2 gon, something in m plus 2 gon will represent Cn. So we said that we're increasing the dimension by 2. So here we're increasing the dimension by 2 as well, meaning we're finding the number of triangles. So originally we have 1 point, and then we increase the dimension, turn it into a triangle. This gives us C1. We only have one triangle here, so the number of triangle in this triangle would be just 1, right? And 2, we expand that into a square, and the C2 here would be, could you guess? Could you guess, Forrest? Are you not there? Okay.
That's 2, right? Or...
Yeah. Okay, here. So there are 2 things. And then for these C3, we're doing a casework. So first of all, let us fix a triangle here. So on the left-hand side here, we have a thing. We have a thing with 4 sides. So we're just taking this here as this indicates the number of triangles we could get. Like the ways to separate a square into several triangles, different ways actually. So this would be C2 times C0, because we do not have anything here. And let us say that C0 is equal to 1, because when we have no object, we have just one way to partition them, just no way. Yeah, one way actually. And so the second case, we fix the triangle in the middle here. And that gives us, we have something with 3 sides here, something with 3 sides here. So that is C1 times C1, right? Because we have this. And the third case would be similar to case 1. Triangle would be here. So that the case here would be C0 times C2. So the total number, the number C3, would be just the summation of all these. And from there, we could have our recurrence for Catalan number. So Cn plus 1 would be equal to 0 C I times I. Okay. This is a recursion. So when we see a recursion, we naturally think about the generating function. So what generating function intends to do is to let all the terms in the Catalan number sequence, let us say that it is a sequence, to be the coefficients before the x to the something. So we will assume that our generating function is Cx, and Cx is an infinite polynomial with all the coefficient being a term in the Catalan number sequence, and attached to it will be x to the nth. Okay. If we simplify this, notice here the recursive formula we get is for Cn plus 1, but the thing here is Cn, so let's do something to it. So we could get something with Cn plus 1. And we will use the recursive formula there. So let us take the first term out. The first term would be just C0 times C0, x to the 0, sorry. X to the 0 is 1, and C0 is 1 as well, as we talked about. So we will just take this one out, and that leaves us this. This is the same as shifting the whole thing here. One place behind. So that gives us, if we take the x out, and this whole thing before, it will just become the Cn plus 1 formula. We're just pushing things once forward, and then the x change because we take one x out. And to further simplify this, I need to introduce you something called Gaussian product sequence. So originally, the Gaussian product sequence is this. You could find this also other places online. Let's just use some different index here. That is equal to a summation of okay, we will use this directly, and the proof, you could think of the proof as shown on the right-hand side in a grid. So we're just plussing things on this diagonals here. So for this diagonal, we don't have the x term. So x term, we could also think of this as x to the 0th. And here we have x to the 1st, and so on. And we're just summing all these together. And also we have the x here, which will be plugged here, here, and here. So we will use this directly. This gets us to something like this. Oops. We do not want this to be N because we do not want to confuse ourselves. Let this be L. Okay. And then this will get us to just our generating function. So this is Cx times Cx. That's Cx squared. Let's do this too. And then this is just a quadratic equation. We could solve C of x in terms of x. This by quadratic formula will get us to 1 plus minus the square root of 1 minus 4x divided by 2x. And then we need to think of whether this formula should be plus sign, should have plus sign, or should have minus sign. So we know that C0 should be 1. And if we use a plus sign here, this will get us to something that's undefined if we calculate the limit when x approaches 0. But if we use the minus sign, it would just get us to the right place if we are taking its limit. So the correct formula should be okay. We will then take this forward to simplifying this whole thing. And before I get to further simplification, I need to talk to you about two formulas that we're going to use. So the first formula is, sorry, let me close this window. Let me just play this. Here, this be better. Okay. So first of all is this formula here. So first, this looks like a very weird thing on the right hand side. What we will do is to derive the right hand side from the left hand side. And left hand side do look a bit more complicated than the right hand side. The right hand side is like perceptually looks like something very sophisticated, but the left hand side is like very chaotic, not mathematically chaotic, but like a lot of expressions in it. Yeah. We'll start from the left-hand side. We naturally want to cancel something out because we have 2n, choose n. This looks like something that we could simplify. Okay, so we keep this part unchanged. Let's see what we could do to the 2n, choose n. We could expand this into a factorial form all the way to 1. And we will have n minus 1 all the way to n1, and then time n factorial reciprocal. Okay, so here we could cancel a lot of things out, but that also leaves us something. This gives us 2, and this gives us, here we will have 2n minus 2. This also gives us 2 and dot dot dot. So the whole thing on the bottom here will just be canceled out. That gives us 2 to the n's on the top because we have n terms here. Okay. And we have a 4 to the n's here. So this 2 to the n's on the top will cancel with 2 to the nth. Just part of the 4 to the n's on the bottom. So this will leave us 2n minus 1, and we have 3 dot 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 all the way to 1. On the bottom here we have n factorial. Okay. And we could cancel this out. We will have a lot of terms with this here. We will just use we'll use 2, -1. So that will be -1 squared, that's 1. This loses -1 because we have 2 to the n's here. Let's move the n factorial here and let this part to combine with the top part on the right hand side here. So this would be 2n minus 3 divided by 2. All the way to 1/2, but we also have one more 1/2 because this comes from -1 to the squared, and this comes from part of the 2 to the nth, because we here we have n minus 1 terms. The 2n minus 1 canceled out, so yeah, that's what we have. And this, if you look at this carefully, this will leave us 2n, which is equal to the right hand side. This is just something by definition. By this. Okay. Let us look at the second thing that we need. I'm also going to write the left-hand side as something much more complicated, like looks having something that has more like terms in it on the left-hand side, and then on the right-hand side, I will put something more precise. We're also going to simplify things from the left-hand side to the right-hand side. Okay, if you notice, we have talked about the Catalan formula that we want to yield. This do look something just like the Catalan number formula. So apparently this is something that we're going to use. Okay. Let's write this because we have 2n plus 1 here. So we want to cancel this out. We will just write just a few parts from this expression here out. We will have 2n plus 1 here, so we could cancel something out. And we want to turn this into this here. So we are going to take something out and make this like 2n k times 2n choose n. So this is the part that we move out. One and plus 1 here. these two cancel out, these two cancel out, these two also cancel out. That's very nice. Okay, we need to notice something um, behind this part. So naturally we will have n plus 1 here. No, yeah, wait. Yeah, and we want to move this part here. Oh, sorry. Keep. And we want this right-hand side to be like 2n, choose n, so that there's one more thing that should be moved out. This part here. So this will cancel out with something on the top from this expression here once we move these 3 terms out. Okay. So that is our expression on the right-hand side. Apparently we can see that. Okay, let's go to the further simplification part. Just a recap from the generating function, we have c of x is equal to 1 minus the square root of 1 minus 4x divided by 2x. Okay. We take the first part out first, and then for the second part, we have this. Okay, this is a bit hard to see, but if we write this expression, this square root expression, in this form, you might have seen something. This is binomial theorem. We could use this. We could apply the binomial theorem to this to simplify this whole thing. Okay. So from this step to the next step, we need to use binomial theorem. And when we are simplifying things with a square root, it's useful for us to think of binomial theorem, although we do not usually think of this as a binomial theorem thing. This only makes things more complicated, but this time, more complicated things makes our life more easier. I just expand this out for you. It's just the binomial theorem. If you could just pause this video and go to find this yourself. Okay, this do look like something from our previous part, but this part here looks a bit complicated. We'll take negative 1 out. I'm just expanding this part into these 3 things. And these 2 gives us 1 to the i, that's just 1. These 2 cancels out. Let us put this 2 inside. So this thing looks a bit more familiar. And then again, from the previous formula that we have, just to simplify this thing, to combine these all together, this leaves us 2i plus 1. Notice here we just put this part inside here. And I also put this inside. So this is just the second expression that we talked about. This is and then from this we could see that Cn would be Cn would be just the coefficient before x to the nth, which is just divided by n plus 1 times 2n choose n. Yeah, that is our Catalan number formula. So that's the end of the proof. And there are actually more visualizations. So the way to divide up n plus 2 gons into several triangles and find different ways of doing that, that's invented by Euler. And if we do that, we could also form some other visualizations that Catalan number is usually represents. So let's say that this is our first triangle that we draw. This is y. And we're expanding this to the adjacent triangles. We have 2 here, the 2 and let's do 2. And then we're expanding this again. This is 4. So this could be written in the form of a tree. So we have 1 here, have 2 things here, then we have 1, 3 here, 1, 3 here, we have a 4. So another way to represent Catalan number is by using tree. And trees and the number of dividing up the n plus 2 gons into triangles are very closely connected, as you could see from here. So here are several resources that I use. The Catalan proof is from Catalan number, from Stanley from MIT. And the question 7 is from Art of Problem Solving. The Gaucho product, you could check out the Wikipedia, and the non-crossing partitions. I learned something from the non-crossing partition, but the definitions came up by myself. So if there are problems, just let me know. Yeah, that's all I have. Forest.
Okay, so now we'll go back to number 6. I'm gonna share my screen and for this. Okay, so just get that tab back up. Okay, so I might have been a bit unclear with the wording of the problem and the diagram, so I changed it slightly. So number 6 asks how many ways are there to get from here to here, and we're going to go only on these ones, not these ones. So we want to start with some slightly smaller cases. So let's say how many ways are there to get to here from here? Because if we think about it, we can ignore this last one, it doesn't matter, and we can ignore this first part, it doesn't matter. There's only one way. So how many ways are there to get from here only going in this general direction? Well, you can go here, and that's about it. We want the shortest path possible, so that's only one way. Now to get to here, we can go this way, or we can go this way. So that's 2. To get to here, we can go here, 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 or here. So that's 5 ways. So I don't think that it would be, I don't know how surprising it would be if I told you, I think that there's 14 ways to get to this point, right? Is it
I
14?
don't know.
Anyway, so so you can do this with direct counting by saying that there's one way to get here, 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 1, 2, 2, 3, 4, 5, and so on. You can do that. But another way to think about it is if you're trying to get from here to here, it's possible that you get 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 here, and you might not, or you might not even hit here at all. Or you could think about it if I turn back this way, moves going south, moves going east, but there have to be more moves going south than east. Like if you go south once and east twice, you end up in a non-valid zone. But if you go south twice and east once, then you're still in a valid zone. So it turns out that this is just another way to find the Catalan numbers, and there's probably a VHV correspondence that will actually link these two methods of finding Catalan numbers together. So, this was the first, and I think this is the first, second, third, fourth. So I think we want the 5th Catalan number is that, and I think that's 42. I'm not exactly sure, however,
Yeah, I think so.
but something related to but
It's
you
42.
can relate this to the Catalan numbers. And there's another proof of the Catalan numbers where if you go past, you just flip everything else over. And I don't remember that proof exactly, but there is definitely a way to show that this is the Catalan numbers. So that's
Yeah.
number 6.
Yeah, this is similar to like this is just non-crossing partition, actually. Or you could think of this as a parentheses. This like problem where we
Parentheses.
have like we must close the parenthesis before getting to another one. So basically the same.
Then number 8. So this one, it seems a bit weird because this one can just go on forever, can't it? And and Bob Duncan is going to be the first one to flip a coin, so like he could just flip heads right away and win. And but there's like a 1/2 chance that he doesn't do that. And Joe Flaw, if he flips ahead, then he automatically wins. And if not, then if John XV flips ahead, then he automatically wins. But if all 3 of them flip tails, then they're back to the beginning. So then that just repeats itself. So you'll actually end up with an infinite series. And for Bob, it's going to be 1/2 plus 1/2 times 1/8 plus 1/2 times 1/64th. And that will simplify to 4/7. And then similarly, Joe Flaw will have 2/7, and John XB will have 1/7. You can also just see that from there's the weightings at the beginning, if would be 4 to 2 to 1, and then the other one just repeats. So it's going to be a 2/7 chance that Joe will win. And then for the number 9, which is going to be the last question that we do, there's 2 people standing on one side, there's 2 people standing on the other side, one person gets removed, and this is not Shaq's theorem because you have to read the question. how many people can catch the ball next, assuming normal Newcomb rules. The ball is on this side because the other person got out. This person has the ball and now throws it, and now we'll throw it over to this side. And either of the two people can catch it. So this is a direct counting problem as well as an English problem. So that is the entire so that is all the discrete A4, discrete B6 problem set that we'll be going over today. Are we going to continue going over the other ones in the future?
I think so.
Okay.
Yeah.
Like some of these questions, they're actually pretty good, like number 12 and 17.
Yeah, I'm going to pause this recording right now.